Chapter 10, Module 3. In this course of algebraic topology, we have seen how to construct fundamental groups of pointed topological spaces and have seen the construction of singular and simplicial homology groups. Certainly, a question arises, is there any connection between fundamental group of a space and any of its homology group? Now, in this module, we shall establish that for path connected topological spaces, the fundamental group and the first homology group are essentially same. One thing we have also seen that fundamental group of a topological space need not be abelian, whereas the first homology group is always abelian. So, we begin with introducing the concept of Abelianization of fundamental group. We define derived subgroup or commutator subgroup of a given group G. Let G be a group and A, B are 2 points in G. The commutator of A and B is the element of the form A B, A inverse, B inverse. We collect all the commutators and call the set capital A consisting of the elements A B, A inverse, B inverse such that A B belongs to G. Then the group generated by this set A is a subgroup of capital G called the commutator or derived subgroup of G, and it will be denoted by bracket G comma G. It is very easy to see that G is commutative if and only if the commutator subgroup is the trivial subgroup identity. If G is commutative, then A is equal to identity, and so the commutator subgroup is identity. On the other hand, if the commutator subgroup is identity, then A B, A inverse, V inverse is equal to E holds for all A B belonging to G, thereby giving A B equal to B A for all A B. So, that means G is commutative. In the next theorem, we see that the derived subgroup of a group G is always a normal subgroup of G, and the quotient group G by the commutator subgroup of G is always abelian. Let us first prove that it is a normal subgroup of G. By the definition of commutator subgroup, we have that all the elements A B, A inverse, B inverse are inside the commutator subgroup whenever A and B are taken from G. Now, it is enough to show that for any G belonging to G, G multiplied by one generator A B, A inverse, B inverse multiplied by G inverse should be inside the commutator subgroup. If we can show this for the generators, then of course, the thing will be true for any element of the commutator subgroup, and therefore, it will be a normal subgroup. Now, if we take G A B A inverse B inverse G inverse and plug in G G inverse in between A B B A inverse and A inverse B inverse. As we know that G inverse into G is always identity element, so that will not affect the element G A B A inverse B inverse G inverse, and so we have this expression that G A B A inverse B inverse G inverse is of the form C D C inverse D inverse, where C is equal to G A G inverse and D is equal to G B G inverse. Therefore, this particular element is inside the commutator subgroup G G, proving that it is normal. Now, to show that G by G G, that means the quotient group formed by G by commutator subgroup of G is commutative. Let us denote the commutator subgroup by capital H for ease of notation. In order to show that G by H is commutative, we need to show that AH into BH should be equal to BH into AH for all AB belonging to G. For any two elements AB belonging to G, we have that BA whole inverse AB is equal to A inverse B inverse into AB, which can be viewed as A inverse B inverse A inverse inverse into B inverse inverse, and that should be an element of the commutator subgroup H. And that means AB into H is equal to BA into H, which implies that the product AH BH is equal to BH AH as desired. More generally, one may show that if we take the commutator subgroup of a group G and H is a subgroup of G, then H will contain the commutator subgroup of G if and only if H is a normal subgroup of G and the quotient group G by H is abelian. Now, we define what we mean by Abelianization of a group G. Let G be a group and we take the commutator subgroup of G. We have shown in our last result that the quotient group formed by taking G by commutator subgroup of G is always abelian. We call this quotient group the Abelianization of the group G, and we denote it by GAB for simplicity of notation. It is clear that the Abelianization of an abelian group is always isomorphic to itself. If G and G1 are two groups such that G1 is abelian, and if we have a homomorphism phi from G to G1, then that particular homomorphism always induces a homomorphism psi from the Abelianization of G to G1 given by psi of x Gg is equal to phi x. That means, if we take a typical element x Gg from the Abelianization of G, then x is an element of G which was mapped via the function phi to the element phi x of G1. Then the new map psi will take that particular element xgg to the same element phi x. First, to check that such a map psi is well defined. For that, suppose these are the two representatives, one is xgg and the other one is ygg. Then x inverse y is an element of the commutator subgroup gg, and that is x inverse y is of the form a1 b1, a1 inverse b1 inverse, so on up to an bn, an inverse bn inverse, which implies that phi of x inverse y is equal to phi of a1, phi of b1, phi of a1 inverse, phi of b1 inverse, and that gives us phi x inverse phi y is an element of the commutator subgroup phi g, and that is equal to identity. But that is the same thing as phi x is equal to phi y. So, psi is well defined. That psi is a homomorphism will follow from that phi is a homomorphism. So, that proves our claim that whenever we have a homomorphism from G to G1, it induces a homomorphism from the Abelianization of G to G1. Now, let us suppose that X is a path connected space and x0 is a point taken from capital X. Our intention is to construct a surjective homomorphism from the fundamental group of X based at x0 to the first homology group H1x. This homomorphism will induce another surjective homomorphism from the Abelianization of the fundamental group of X based at x0 to H1x. To show that such homomorphism is actually an isomorphism. This particular isomorphism is called Hirovitz isomorphism. And if we can prove that, it will establish a very important connection between fundamental group and first homology group, that the Abelianization of the fundamental group of a path connected space is isomorphic to its first homology group. It is important to note that the result which we are going to establish now requires the space to be path connected. If the space is not path connected, the result may not hold. Let us take an example. Suppose the space is the disjoint union of two circles. If we construct the fundamental group of this space, then it is the infinite cyclic group Z, but its first homology group is the direct sum of two infinite cyclic groups Z with itself. So, with this we try to prove the result for path connected spaces. Suppose capital X is a path connected space. Choose any point x0 from capital X. We wish to construct a homomorphism phi from the fundamental group of X based at x0 to H1x. Firstly, we observe that the closed interval I can be regarded as a subspace of R2 by treating the closed line segment joining 1 0 and 0 1 as a copy of I. In view of this, a path alpha can be viewed as a singular one simplex alpha from the standard one simplex delta 1 to x. Moreover, if alpha is a loop, that is alpha 0 is equal to alpha 1 equal to the base point x 0, then the one simplex alpha is always a one cycle. To prove this, we consider the portion of the chain complex as follows. The homomorphism, the boundary homomorphism delta 1 is in between C1x and C0x, and if I take alpha from Z1x, where Z1x means the kernel of the homomorphism delta 1, and so alpha belongs to Z1x implies that delta 1 alpha is equal to 0. Now, delta 1 alpha at the point 1 is equal to alpha compose D01 minus alpha compose D11, and that is equal to alpha 10 minus alpha 01, which is equal to 0, because we have alpha as a loop, and therefore, alpha 10 alpha 01 both will coincide with the point x0. In view of these observations, we define a map from pi 1 x x0 to H1x very naturally as follows, that if I take a class alpha from pi 1 x x0, then phi of alpha is equal to alpha plus b1x, where alpha plus b1x will be denoted by alpha bar for simplicity of notation. We need to show that phi is well defined. For that, we start with two representations of an element of pi 1 x x0. That means, class alpha is equal to class beta inside pi 1 x x0. Then alpha is path homotopic to beta based at x0. Suppose capital H is a path homotopy between this alpha and beta. We have to find some tau from C2x such that delta 2 tau is equal to alpha minus beta. Now, I cross I is a rectangle. We can think of that rectangle as the geometric realization of a simplicial complex K described here, having the vertices as A0, A1, A2, A3, the one simplexes as A0, A1, A1, A2, A0, A2, A0, A3, A2, A3, and the two simplexes as A0, A1, A2 and A0, A2, A3. The following diagram helps us to visualize this situation much better. We have a rectangle with the vertices A0, A1, A2, A3 and the lines joining the vertices as shown in the diagram are the one simplexes, and the two triangles thus formed, one is A and the other one is B, are the 2 simplexes. Here we identify the rectangle I cross I with this particular rectangle I1 cross I, where I1 stands for the line segment joining 0 1 with 1 0. The 2 simplexes A0 A1 A2 and A0 A2 A3 can both be viewed as copies of a standard 2 simplex delta 2. Hence, if we call A0 A1 A2 as sigma 1, then sigma 1 is actually a singular 2 simplex from delta 2 to mod k, and sigma 2, which is A0 A2 A3, is also a singular 2 simplex from delta 2 to mod k. So, the following diagrams show that H compose sigma 1 and H compose sigma 2 are singular 2 simplexes of X. We already had that homotopy capital H from I cross I to X, and sigma 1, sigma 2 both are continuous functions, and thereby H compose sigma 1 and H compose sigma 2 are 2 continuous functions from delta 2 to X, and therefore, they are singular 2 simplexes. So, we consider tau as the sum H compose sigma 1 plus H compose sigma 2, and we know that it will be a member of C2X. We claim that delta 2 of tau should be equal to alpha minus beta. Before we prove this, we observe that the function h restricted to 0 cross I and the function h restricted to 1 cross I are constant maps at the point x0. This follows from the fact that h is a path homotopy between the loops alpha and beta based at x0. So, viewing H composed A0 A3 and H composed A1 A2 as singular 1 simplexes, as we did for H composed sigma 1 and H composed sigma 2, we get that H composed A0 A3 operated on the point ST is equal to x0, and H composed A1 A2 operated on ST is again equal to x0. So, delta 2 tau ST is equal to tau composed D0 on ST minus tau composed D1 at ST plus tau composed D2 at ST, and that is equal to tau of S0t plus tau of ST0, and that is equal to H composed sigma 1 of 0 ST plus H composed sigma 2 0 ST minus H composed sigma 1 S0t minus H composed sigma 2 S0t plus H composed sigma 1 ST0 plus H composed sigma 2 ST0, and that is equal to H composed A1 A2 minus A0 A2 plus A0 A1 on ST plus H composed A2 A3 minus A0 A3 plus A0 A2 on ST. But cancelling the similar terms, then we have H composed A0 A1 plus H composed A2A3 at ST, and that is equal to alpha ST minus beta ST. And this proves that the function which we have defined here is well defined. That phi is a homomorphism follows easily from the following theorem, that if alpha and beta are two loops based at x0, then alpha star beta plus b1x is equal to alpha plus b1x plus beta plus b1x. The proof of this theorem follows straight away if we look at the diagram. This diagram helps us determining a singular 2 simplex sigma such that delta 2 of sigma is equal to alpha star beta minus alpha minus beta. So, we can define a homomorphism psi from the Abelianization of pi 1x to H1x with the help of the given homomorphism phi. Denote the commutator subgroup of pi 1x x0 by G, then any element of pi 1x ab is denoted by class alpha by G, where alpha being a loop based at x0 can be viewed as a one cycle. So, alpha bar is a member of H1x, and hence we define the function psi from pi 1x ab to H1x by sending the typical element class alpha by G to the element alpha bar. We now define a homomorphism eta from H1x to pi 1x ab and show that such eta is the inverse of psi, proving that psi is an isomorphism. Choose any path Wx starting from x0 and ending at x whenever x is not equal to x0. Wx0 will stand for the constant loop at x0. For any singular one simplex sigma, if sigma 0 1 is A and sigma 1 0 is B, then WA star sigma star WB inverse is a loop based at x0. In particular, if sigma is a one cycle, then sigma 1 0 is equal to sigma 0 1 and that is equal to say A, then in such case WA star sigma star WA inverse is a loop based at x0. Hence, we define lambda, a map from S1x to pi 1x ab, where S1x stands for the collection of all one simplexes of x. Now, we define lambda by sending an element sigma of S1x to the element of pi 1x ab represented by the loop WA star sigma star WB inverse and then extend it to C1x by linearity. That means, define lambda from S1x to pi 1x ab by lambda sigma equal to the class WA star sigma star WB inverse by G and extend by linearity to C1x. Of course, it is not hard to see that lambda is a homomorphism. If delta 2 is the boundary homomorphism from C2x to C1x and lambda of delta 2 of S2x is equal to 0, then we can define a homomorphism eta from H1x to the Abelianization of pi 1x in a very natural way. So, we proceed to show that lambda of delta 2 S2x is equal to 0. Let us take epsilon, a singular 2 simplex in X. We shall show that lambda of delta 2 epsilon is equal to 0. Let epsilon of 1 0 0 is A, epsilon sends 0 1 0 to B and epsilon sends 0 0 1 to C. If di from delta 1 to delta 2 are the maps that insert 0 in ith place, we get lambda of delta 2 epsilon is equal to lambda of epsilon composed d0 minus epsilon composed d1 plus epsilon composed d2, and that is equal to the class WA star epsilon composed d0 minus epsilon composed d1 plus epsilon composed d2 star WA inverse by G, and that has to be equal to 0 because WA star epsilon composed d0 minus epsilon composed d1 plus epsilon composed d2 star WA inverse is a constant loop at the point x0. Hence, we get that image of delta 2 is contained in the set kernel of lambda. Now, we define eta from H1x to pi 1x ab by eta of sigma bar is equal to lambda sigma. Since sigma is a one cycle, we have sigma 1 0 and sigma 0 1 as the same point A, and therefore, lambda sigma will be the class WA star sigma star WA inverse by G. We now show that the map eta is well defined. Let sigma 1 bar is equal to sigma 2 bar in H1x. Then sigma 1 minus sigma 2 is a member of image of delta 2, which we have already proved that it is a subset of kernel of lambda, and therefore, lambda on sigma 1 minus sigma 2 will be the trivial element. So, the class WA star sigma 1 minus sigma 2 star WA inverse should be inside the commutator subgroup G of pi 1 x, and that means class WA star sigma 1 star WA inverse by G is equal to class WA star sigma 2 star WA inverse by G, and that means lambda sigma 1 is equal to lambda sigma 2, and that proves that eta is well defined. That eta is a homomorphism is clear from the fact that lambda is a homomorphism, and it can be checked, and it is not very hard to see that such eta is the inverse of psi, which we have already defined earlier. And this shows that Chi is an isomorphism. Hence, for a path connected topological space, first homology group and the Abelianization of its fundamental group are same. For path connected spaces, sometimes construction of fundamental groups becomes very difficult, but it is often seen that homology groups are easy to compute. In such situation, Hirovitz theorem helps. In fact, Hirovitz theorem gives a connection between higher homotopy groups and the homology groups. This theorem is very much useful and has immense application in higher dimension. With this, we end chapter 10 and our course on algebraic topology.